All right, so thanks for returning. So I want to start out with just a quick reminder of the kind of arguments we talked about last time. And I'm going to do a slightly different argument. I'm just going to put it up here. It might already be available to us. So let's say x is a normal. And remember, CM for me means Cohen-Macaulay variety. And let's say we're working in characteristic P. And let's suppose H inside X is some kind of reduced Cartier divisor. So this just means, it's, reduced Cartier divisor. I mean, I don't really need any of this to write what I'm going to write, but I don't want to make people confused. And I don't want to just stick with smooth varieties because this talk is about non-smooth varieties. And remember, we have this map which we wrote as Fe lower star omega x to omega x, and this is dual to the Frobenius Ox to Fe lower star Ox. Okay. And finally, just in this context here, we actually have a short exact sequence, 0 to omega x twisted by h. And you could write this again as Ox, if you'd like, more divisorially, Ox kx plus h. And this maps to omega h, and that maps to 0. So we have a short exact sequence. Okay, so we sort of implicitly used this sequence in our Seshadri constant argument last time. But I just want to remind you that we have all this sort of material in front of us. Now, if I whack this sequence with cohomology and also keep track of the Frobenius actions and everything, I get this diagram right here. All right. Now, if x was smooth and we were in characteristic 0, or even if x had rational singularities and we're in characteristic 0 as we saw last time, this H1 right here, this is just that sequence with cohomology applied, this H1 would vanish by Kodaira vanishing. What? Oh, and L, yeah. L is ample, thanks. Absolutely, that would vanish by Kodaira vanishing. But in characteristic P, we don't have that necessarily. But at least in some cases, we had a replacement. And the replacement is up to Frobenius, we sort of do. So we have all these maps going up here, right? And we do have this vanishing right here, okay? So even if this is not 0, this one is 0 right here. This diagram, of course, commutes. And there's a quick observation I want to make here that's kind of useful. Regardless of what x is here. Let's say h is, I don't know, f split. Okay? If h is Frobenius split, that means this map here is split surjective. Okay? And if we do the chase here, if I take, if I'd like to show somehow that elements here lift to there, well, every element here comes from here. And this map's also surjective. So if I have an element, it comes to here, comes from there, and suddenly I have this chase. And therefore, every element here, z, actually lifts to there, if x is Frobenius split. This is very much like what we did with the Seshadri constant argument. And in fact, on the other hand, like if the element z you cook up is cooked up with a Seshadri constant argument, it also lifts, because it also comes from this Frobenius image. Remember, if we had some kind of Seshadri constant condition of L at z being bigger than the dimension, then we knew not only was there an element there, but you can actually find it in some way. And there's other ways like this, that elements that come from this kind of Frobenius image sometimes behave as though Kodaira vanishing is true. In particular, they might come from here. Okay, so if you're playing around with this kind of thing, you might start to say, okay, well, that seems like it's useful. And actually, this kind of argument, and even this Ashadri constant business, showed up in Haken and Zhu's, existence of flips argument for characteristic p bigger than 5 dimension 3. So this kind of argument does show up in characteristic p birational geometry. But you might stare at this and you say, okay, well, when is that not true? Right? I mean, not everything is Frobenius split. We saw last time that general type varieties can't be Frobenius split. But still, maybe this might be true. And there are both, in fact, global and local conditions for when this might be true, for when you might be able to pick up something. And so what I'm going to talk today mostly is local criterion for when things are in the image of this kind of map. So, for example, if Fe lower star omega x to omega x is not surjective, then, especially for very ample L, sections, or maybe I should say H here, then global sections of H naught, omega H, L restricted to H, that aren't in that image, that don't land in this image, aren't in the image, they won't be suitable for this kind of argument. Right? Does that make sense? If I have an element that cannot be in this image because this map is not surjective, then there's no way I can lift it using this argument. I'm not saying anything deep. Okay. Lifted via our argument. And so I think this at least brings us to our first question that we're going to consider is when is this map at least locally surjective? Okay. All right, question mark. Okay, so we've already seen that if X is Frobenius split, it's always locally surjective, right? Because this is the dual to a split injection, so the dual of a split injection is going to be a split surjection, and this is going to be, okay, so it's okay if X is Frobenius, F is for Frobenius split. Okay. But what else do we expect? All right, so what I'm going to do now, and I think this is my motivation based on the previous talk, is I actually want to sort of get into what this map looks like, what it means, and what kind of things we can expect. Okay, so I'm going to begin by recalling the following theorem of Kuntz. I think many of you probably know this. Let's say Y is a variety. Let's say over K, and I'm going to assume K is perfect. Okay? Then Y is regular, or because I'm over a perfect field, smooth, if and only if Fe lower star OX is locally free for some or all E. So being non-singular is actually the same as some kind of local freeness of the Frobenius push forward of your structure sheaf. It's a good exercise if you haven't thought about this before to figure out what vector bundle you get on like P1, right? If you push forward by Frobenius of O, what vector bundle you get? You know it's going to be a direction of line bundles. Which line bundles? Okay, and I'm not going to give a proof of this, but maybe I'll say just a little bit about yeah, I'm not going to give a proof of this. But I do want to say just a little bit about the proof. Essentially, you know, if you're trying to go from regular to locally free, well, how would you normally do it? Well, what about a polynomial ring? Is that okay? And if you just write down the polynomial ring, you actually see it's actually free, and it's easy to write down the basis in terms of monomial, basically the toric setting. And so that's, but we'd like to do a little bit better. Okay. And what happened to my eraser? Okay. So, whoops, Wyatt, I can tell everyone's asleep after lunch. Because no one even pointed out that my y should be an x. All right, so the first thing I want to point out here, and maybe I'll actually write it on the clean board to start, is that if I'm locally free, then if I look at a stock, this is a free OY module. And so there's going to be lots of different projections onto various summands to the stock. And so this is going to be projection. In particular, it's going to be some kind of projection onto a summand. And you might ask, if you haven't thought about this stuff before, is this a splitting of Frobenius? And the answer is probably not. Because I might have projected onto the wrong summand. I mean, how do I even know I can write the thing generated by 1 as one of my summands? And you can, but it requires a little bit of thought. But how about, let's just say I gave you a surjective map here, and I just want to show you that giving you any surjective map here gives you a local Frobenius splitting, which is certainly going to give us that surjectivity that we were sort of interested in up there. Okay, so if I have a surjective map right here, say surjective, well, what can I do? Well, I know it's surjective, so it has to send something to 1. Maybe it sends some r to 1, little r. Okay? And the problem is, maybe I have OYY, I have the nice little Frobenius up to there, but 1 doesn't go to r. Maybe 1 goes to something that gets sent to 0. Right? So it's probably not a Frobenius splitting. But on the other hand, I can always factor this. I can map it by Frobenius first. This is just Frobenius. And then I can look at the map basically that sends 1 to r. And now if I trace through this map, 1, this is just Frobenius. I'm trying to show a Frobenius splitting. 1 goes to here. 1 now goes to r, and now r is going to get sent to 1. So, what does this say? This says oops, I'm losing my. So if I have a surjective Fe lower star OY Y to OYY, then there exists a Frobenius splitting. Okay. And sometimes it's a little bit easier to work with these surjections a little bit more generally, at least in some cases. Okay. So if I have one of these surjections, in particular if I'm regular, then I'm definitely Frobenius split, and this map over here is definitely surjective. All right. And so essentially it came out in commutative algebra, but also actually commutative algebra and in the study of Schubert varieties and certain kinds of representation theory, that Frobenius splitting actually tells you quite a lot about singularities. And you can consider various notions of singularities measured by how close Fe lower star OY is to being a free OY module. So here we have Fe lower star OY. We're asking, is it locally free or not? And there's various ways you can weaken that. One thing you could hope for example, that we've already seen is useful, is we could ask, is it F split? Or at the very least, is it locally F split? And the first thing you might discover is, well, or the first thing you might run into if you start thinking along these lines and looking in the literature, is you might run into this class of singularities called F pure, which is just another word for locally F split. Okay? All right. So if I'm F pure, that's another way for me to say I'm locally F split. Sorry to introduce the terminology, more terminology, but here we go. All right. F pure, locally F split. Maybe, especially in the Cohen-Macaulay case, we'd like to give a name to that surjectivity of Fe lower star omega h to omega h. That seems like a reasonable thing to do. So that surjectivity, because it's surjective, we give it the very straightforward name of F injective. Okay? So ones that are surjective, we call F injective from here on out. So you might ask why we do such a thing, except, to play a joke on everyone learning the field. No, F injective was originally phrased in a dual setting of local cohomology. And then the surjectivity on omega h is phrased as an injectivity of Frobenius on local cohomology. And we've already seen that F pure locally F split implies F injective. And I'm actually not gonna tell you what F regular is at all during this talk. I will say what F rational is a little bit later. I'm gonna write this here. But you might be asking, okay, well, what kind of things are in this row or this row, and what's this difference here? I think maybe this difference right here you shouldn't think about so much. I mean, they're actually equivalent if you're Gorenstein or what's called one Gorenstein or quasi-Gorenstein. If omega is locally free, they're actually the same notion. i.e., okay, actually, let me put it this way. If omega is locally free, then locally this looks like OX, and I gave you a surjection from Fe lower star OX to OX, and I just proved to you that if I give you a surjection, that actually gives me a splitting. So in the case that it's locally free, F pure and F inject, omega is locally free, F pure and F injective are the same. And so what should you think about for this row? Well, the standard thing to think about is maybe this, there's a big difference between these for cones, but I think the right thing to think about for this talk anyways is cones over ordinary abelian varieties are the ones that satisfy that row. Okay? Cones over abelian varieties are not going to be F regular, and actually they won't be F rational either, but they're not going to be F regular. But on the other hand, at least if I take a Fano variety, reduce it to characteristic P for P big, I take the cone over a Fano for P big, that's always going to be this row, and we'll get to what these are, at least F rational, in a little bit. Okay. And you might ask, that's a lot of singularities to be introducing us to at this point. And I think what I'd like to do is I'd like to say these singularities are very closely related to a bunch of other singularities you've heard about in other talks. And what I'm going to mostly do today is explain sort of the relation between singularities defined by how close I am to being Frobenius split here, and the singularities that we've been hearing about in standard birational geometry. And here some of them are anyways. I've left out canonical and terminal singularities. They're up there somewhere. But the point is somehow that the diagram I drew over there is actually analogous to this diagram right here. All right. And I am including this, again, if you're not familiar with these singularities, maybe it's better just to focus on one or two of them. We've been hearing a lot about log canonical or semi-log canonical singularities. It turns out those are very close to F pure. And I'm actually going to give a proof of at least part of that relationship in a little bit. So semi-log canonical, very close to F pure. Dubois, heard about that in Janos's talk this morning, very, very close to F injective, at least conjecturally. Rational, F rational, you might have guessed that based on the name. And then this log terminal, again, that we've heard about is actually quite close to F regular. And again, the same kind of analogy holds here. This line, top line, you should think of as like cones over Fano varieties. You're thinking about hypersurface singularities. The number of variables should be greater than the degree, and here the number of variables is greater than or equal to the number of than the degree. Maybe is what you might think of. Okay. All right. So my goal, at least for a little bit longer, is to tell you a little about this F pure, this F split semi-log canonical connection. Okay? And give you some idea of why these things are so closely related. Okay. I'm going to leave those. Actually, I can probably flip them up here now. All right. So, because I'm looking at singularities, I'm going to switch now from like projective varieties and writing things in terms of stocks to switching to ring notation. Okay? So, let's say R is a normal local ring characteristic P, and I'm going to assume that Frobenius is finite. Turns out the fact that Frobenius is finite implies that R, if you're worried about such things, it implies R is excellent. That's a result of Kunz. It implies it's actually a quotient of a regular ring and hence has a dualizing complex as a result of Gaber. So if you have a normal local ring characteristic P and Frobenius is finite, it's a pretty nice ring. So I guess is all I'm saying. And let's say I give you a map, some phi in. All right, I need a little bit of time to explain this notation here. Fe lower star RR. Okay, this is not the push forward in the category of rings or anything like that. But it is an abusive notation where it just means R is an R module, but we understand the R module action via Frobenius. Okay? So we are just abusing the notation from sort of the scheme theory and putting it right there. Okay, so, and I give you some kind of phi in there. Maybe it's a Frobenius splitting. I do probably want to assume it's not 0 because that would be particularly boring. Okay. And if you think back to last time, we actually saw that in the case that we, instead of R, we had like OX there, we saw that this Hom set was isomorphic to Fe lower star OX, then some twist of the canonical divisor. And if you write that down, I'm going to write it down right here, what you're going to get is Fe lower star. I'm going to write it in a couple different ways. I can write it to the 1 minus p to the e, and then if I'm using Janos's notation, I could double dualize. If you're in commutative algebra, you would put round brackets around, which would mean symbolic power, which is the same as Janus's square bracket notation. Which is not what commutative algebraists write. You also might write this again as F e lower star r 1 minus p to the e kr. I'm out of notation in there, but it's really just canonical to the 1 minus p to the e power. Okay. So in particular, any choice of phi, and this is global or local now, determines, remember phi is not 0, so if I give you a non-zero section of something, some twist of a divisor, this is going to, so phi determines some maybe d phi, and this is going to be linearly equivalent to 1 minus p to the e canonical divisor of r, spec r. Okay? So it determines some divisor. I don't like the erasing. I'm going to try a different one. All right. I'm gonna go with it. At least it's uniform. Okay. So every time I choose a Frobenius splitting, and this is something especially the Frobenius splitting crowd has known for a long time, every time I choose a Frobenius splitting, I'm also picking a divisor, and if I give you such a divisor without linear equivalence, I'm actually choosing a Frobenius splitting up to multiplication by a unit. Now, there's reasons why you might not want to, remember d phi is linearly equivalent to 1 minus p to the e kr, you might want to sort of normalize with respect to p and e. And so what you might define is you might define delta phi, and this is going to be equal to 1 over p to the e minus 1 d phi. And this is going to be q linearly equivalent to negative the canonical. Okay. Or in other words, kr plus delta phi is q linearly equivalent to 0. And so this is the boundary divisors that have sort of shown up in some other contexts. Okay, so what I'm saying is any choice of a map right here determines a q divisor. These are q coefficients. I'm dividing by something with the property that kr plus delta phi is q linearly equivalent to 0. Okay. I think I decided the other erasers are better. Okay. Any questions so far? No. So, even if you're thinking about birational geometry, you might ask, well, why do we have all these divisors, delta phi, lying around? And there's a number of decent reasons for that. The birational geometry people were in characteristic 0. They didn't have any Frobenius splittings to associate, their divisors to. So why do they have these delta phis even in characteristic 0? And I think there's at least 3 reasons that I thought of. So, you've heard about this Kalamata-Fifag vanishing, or Kodaira vanishing. The formulation of Kalamata-Fifag vanishing actually gives you a stronger vanishing theorem because you can sort of, if your divisor has nice singularities, like KLT singularities, the Kalamata log terminal, top left corner of my drawing, then it gives you some perturbation room. Maybe you're not ample, but if you're pretty close to ample, up to some kind of KLT divisor, then you can still get some kind of vanishing. So maybe you get improved vanishing. In characteristic 0. They're actually used in a lot of arguments to cook up sections of omega x tensor L. Again, mostly in characteristic 0, but there's a bigger condition, and this is the one I think is most important. And I do want to focus on both in characteristic 0 and characteristic B. So Q divisors, KR plus delta Q linearly equivalent to 0. Effective divisors. So, and what's the number 3 here? Well, the number 3 is they basically let you keep track of canonical divisors as you change variety. And so this is something I think we all know. If I have like a map of smooth curves, I can relate the canonical on the top to the canonical on the bottom by a ramification divisor. Right? And so actually, these deltas can actually be used to do that. And very frequently, especially for blowups, for birational maps, they're used in exactly that way. Okay, so I want to write down just a little bit about this. I want to keep those things up. But I want to write down 1 or 2 really quick examples of this. So I'm going to start out with this curve example, or for this finite map example. Okay. So let's do a quick example. And again, it's just to help you understand how this divisor and map correspondence works. Okay, if I have f from z to maybe y, finite surjective between normal varieties, and characteristic P, maybe I have phi from, I'll be nice, maybe it's like a Frobenius splitting, or maybe I hope it's a Frobenius splitting from OY to OY. I use that to cook up some kind of delta phi, just like that over there. And then let's see, I can write kz equals pullback of ky plus the ramification divisor. I'll call it ram, because I'm probably using every other notation already. Okay. And then what you can do is I can write, let me just write this really quick. I can rewrite this formula right here as kz plus pullback of delta phi, okay, minus ramification divisor. That this is going to equal pullback. I can always do, whoops. Yeah, I'm just adding pullback of delta phi to both sides. Mm-hmm. Okay, and I'm moving the ramp to the other side. So what I have is I have kz plus something is the pullback of ky plus something. And this something right here, maybe I'll call that delta z. All right. Okay, so I have a pair, y delta on y. I can pull it back to z, and I'm going to get the pullback of ky plus delta is kz plus something else, some other term. Okay. I'm calling it delta z to help me keep track of it. It turns out, let's say this is generically separable. It turns out in this case that delta z corresponds to the unique extension of phi to, maybe I'll call it phi z, fe lower star oz to oz. And again, this might be something you're a little bit comfortable with. If I have some kind of map from fe lower star oy to oy, well, oy lives inside oz, I can ask, well, does my phi extend? Maybe it does, maybe it doesn't. If it exists, and that's actually equivalent to this delta z being effective. So you can also use these kind of delta pairs to keep track of whether, as I change from one variety to another, whether or not Frobenius splittings extend, or things like Frobenius splittings extend. Okay. Okay. You know, if it doesn't exist, maybe it only extends, like maybe it doesn't map OZ to OZ, it like maps it into the fraction field or something, and that still works fine. You just have to view it as like then you'd have a non-effective divisor. If you want to go in that direction, that's okay. But the point I'm trying to make here is that this extension of Frobenius splittings does correspond to this extension of varieties here. It's very explicit in the finite map. And you might be a little less familiar about what happens for like birational maps if you're not already into birational algebraic geometry. But let's look at the birational case. Sort of the same picture. So let's say I give you pi from y tilde to y. Let's say this is proper birational. Okay? I can still write ky tilde plus some delta y tilde, and I can write this as the pullback of ky maybe plus delta phi. Okay? And again, the same relation holds. You might ask, if I have this thing like a Frobenius splitting right here, does it give me a Frobenius splitting on the blow-up? Well, more or less, it does, although there's some effectivity concerns here. But at least if I can make, yeah, I mean, that's right. At the very least, if I have one, it certainly corresponds to this delta y tilde. Okay. So, I have this nice diagram up there. So what's semi-log canonical? What's log canonical? We maybe already have seen this, but let me write it down, the definition one more time. Definition, I'm just going to talk about the log canonical version, so the normal version. Everything is fine in the non-normal version, but the technicalities are not useful. So what's my definition? Y delta y, or y delta, I don't know, I'll call it delta phi. I'll just call it delta. I'll call it delta y. This guy is log canonical. If, when I write ky tilde plus delta y tilde is the pullback of ky plus delta y for any birational map, I have, or if we have a resolution, is enough to check on one resolution. For any birational map, I have the coefficients of delta y tilde are all less than or equal to 1. So you could view this as a definition of log canonical. If you want a definition of Kalamata log terminal, it's strictly less than 1, instead of less than or equal to. Okay, how does this relate to Frobenius splitting? Well, if you play around with Frobenius splitting, and if someone asks me at the end of my talk to do it, I'll certainly do it, or maybe it'd be better if I did it privately. It turns out I guess I can write this here. I don't need this anymore. So it turns out that delta phi, the coefficients of delta phi being less than or equal to 1, this is equivalent to phi being surjective in codimension 1. So remember, phi being surjective was like being Frobenius split. The very least you could have as for surjectivity in codimension 1. Okay? So I am telling you that log canonical, at least in characteristic P, is kind of like saying that when I extend the map to any blowup, at least on the locations where it's defined, it's surjective on codimension 1 everywhere. At the very least, that's not equivalent to Frobenius split, certainly. And there's one good reason it's actually really not equivalent to being Frobenius split, is because surjectivity upstairs doesn't apply downstairs, because push forward's not right exact. But if you follow this line of reasoning just a little bit further, if you stare at it for just a couple minutes more, you deduce this theorem, which was originally proved by Hara and Watanabe, although maybe I should, which is that if R, if R is F split, I didn't quite phrase it this way, so maybe I should also say Smith myself. If R is F split, then there exists some delta, and it's actually a delta phi, just like we constructed, and I erased it, sorry. Just like we constructed out of our phis, then there exists a delta phi bigger than 0, such that our delta phi is log canonical. Okay? So if I'm in a fixed characteristic, then if R is F split, then I can cook up a delta phi to make this pair log canonical. The delta phi I pick is the splitting up to some choice of scaling. And again, the way you prove it is basically say, okay, well, if I take my phi, if I extend it to a resolution, if I had a splitting downstairs, it's still sort of got to be a splitting upstairs. It's got to send a 1-to-1 anyways. What does that mean in codimension 1 of the resolution? It actually tells me something about this divisor, and what it tells me is that the coefficients are less than or equal to 1. That is the definition of log canonical. Okay, so you might start to ask, and I've already told you the answer, what about the converse? What if I start out with something that's log canonical in characteristic P? Is it F split? The answer is no. I've already hinted at this over here, F pure locally F split. Cone over an ordinary abelian variety, well, those are all log canonical. They're all F split. But cone over a supersingular abelian variety, cone over a supersingular elliptic curve, still log canonical, but it's not F split. And actually, if you think through what happens, if I take sort of my map that should be a Frobenius splitting downstairs, and I lift it up to my blow up of the cone point, blow up to my resolution, it's surjective upstairs, but when I try to push it down, surjectivity is not preserved under push forward or under global sections. And that's what goes wrong. Okay. But there are some conjectures in this direction. Maybe I'll state one or two of these. Actually, here, let me state a corollary first. If R delta is a pair in characteristic 0, and again, Kr plus delta, delta is bigger than 0, is Q Cartier. And it has the property that maybe when I reduce it to characteristic P, so R mod P, delta mod P, maybe this is some delta phi, which depends on P, is F pure. And this pair being F pure just means the phi, which corresponds to the delta phi, is a surjective phi. Is F pure for infinitely many, or for a Zariski dense set of models I'll explain what I mean by a second, of models, then our delta in characteristic 0 is LC log canonical. And this is actually a direct corollary from that. So in particular, if I have something in characteristic 0, and let's say it's defined over the integers or rational numbers, say, I can view it over the integers, I can go mod p, and I'm basically saying it for all but finitely many p's, or actually, I'm sorry, for Zariski dense, if there's infinitely many p's that make this pair F pure, i.e. the phi corresponding to the delta, if there's infinitely many p's that make it F pure, then our delta is log canonical in characteristic 0. It's basically because it's going to be log canonical in characteristic p, and it's going to extend up. Okay. But now you really might ask about the converse. What if I take something in characteristic 0, like a cone over an elliptic curve, and I reduce it to a family of characteristic p models? And you might know that for an elliptic curve, you know, at least for, you know, for infinitely many p, it's ordinary, and infinitely many p, it's supersingular for an elliptic curve. And so this actually might be something you really might expect, the converse. You might really hope for that the converse is true. We don't know that the converse is true. It's really quite wide open. Basically, the converse is equivalent to the statement that if I have a smooth projective variety, and this is due to Mustatsa and Srinivas, there's Mircea, that if I have a smooth, well, it's not quite equivalent to the Dubois F injective one is. But it certainly is, the converse to this would be implied by if I had the following statement, if I had a smooth projective variety in characteristic 0, and if I reduce it to characteristic p, and I look at the Frobenius action on the cohomology as a bijective for a bunch of p's, for infinitely many p's. If that's true, then this is true. And likewise, I certainly didn't define Dubois, but if that's true, you also get Dubois and F injective being linked up the same way. Likewise, again, if I take something in characteristic 0, and I reduce it to characteristic p, and if I'm F injective a bunch of times, then I'm actually Dubois in characteristic 0 as well. But again, the converse is hard and it's open. Okay. So, however, the picture on the top row is a little bit better. a little bit more fully understood. And I want to state that, and then I just want to say a couple words about some computations. Okay. Let me give you a quick definition. R, again, a ring, characteristic P, Frobenius is finite. R is F rational if two properties, R is Cohen-Macaulay, and if I look at the Frobenius map, this canonical map, this has no stable submodules. This is not the original definition of F rational. It's basically due to Karen Smith. But if I have something that's F rational, that's equivalent to saying R is Cohen-Macaulay. And when I look at this dual map we've been talking about the whole time, it's saying that this has no stable submodules besides 0 and omega R itself. Okay? Some kind of simplicity statement. Okay, remember our rational definition. Rational was kind of similar to that. We also had Cohen-Macaulay, and we replaced that having no stable submodules to push forward of omega y tilde, a resolution was omega y. That was our definition of rational from yesterday. So at some level, they look pretty close. And it actually turns out it's really not very difficult at all to prove that they're the same, or at least to prove that F rational implies rational. Theorem, this is Smith, F rational implies rational. This used to be called pseudo-rational, but Chandor proved that it's the same as other definitions of rational, so I'm just going to prove it rational. F rational implies rational in characteristic P. And the proof is really easy. The proof is pi lower star omega y tilde inside omega y is stable under F lower star omega y to omega y. And the proof of that fact is if I have my resolution, there's a square I can draw where I have Frobenius on the resolution and Frobenius on the base. So this holds, and it immediately follows that if I start with something in characteristic 0 that has the property that after I go to characteristic P, it is F rational, then it is rational in characteristic 0 to begin with. But in fact, there's a somewhat stronger theorem, and this is due to Hara and also Mehta Srinivas. And it says that if R in car 0 and has R mod, okay, R in car 0, yeah, rewrite this. R has rational singularities in characteristic 0 if and only if R mod P has F rational singularities for a Zariski dense set of models. Okay, I'll just write for all P big. And by that I mean for a Zariski dense set of models in my reduction to characteristic B. So that's actually a lot better than what happened in the F pure F injective case, where we only had one of the implications. But for the F rational, actually you have both implications, likewise for the F regular and Kalamata log terminal. And you might ask, okay, great. That's nice. Did they seem nice? And there are actually lots of other connections between these pictures as well. But what I'm going to talk about for the last couple minutes here, and also a bit of next time, is that it turns out that there's some effective ways that we have of checking whether a variety in characteristic P is like F split or F rational, or F regular, or F injective, that are actually, at least I think, are quite a bit easier than taking resolutions, or goodness sake, smooth hypercovers to compute Dubois singularities and doing some computation with those. And so I'd like to conclude by just giving you a tool. Maybe I'll just do the F pure case about how to show a variety is F pure. So that's locally F split. I think that's what I'll conclude with. And then I'll say maybe one or two quick words about what's going to happen tomorrow. Okay. Because tomorrow I'm going to leave both characteristic 0 and characteristic P. I'm going to move into mixed characteristic, which is like over Z, or ZP, the p-adics. We'll sort of look at what happens in those kind of worlds. Okay. We'll talk about inversion of a junction and all sorts of fun stuff. Okay, so theorem, and this is due to Richard Fetter. And let's say I have R is S mod I. Let's say S is a polynomial ring. K is like a perfect field or something again. Then R is F pure at some maximal ideal M. I guess that's an M spec. If and only if the following condition holds. All right. I'm going to explain this notation because it definitely does not coincide with the birational geometry notation. I to the square bracket P to the E colon I, and again, this colon may not be so familiar to some people too, is not contained in M to the square bracket P to the E. Okay, so let me tell you what this M to the square bracket condition means. So I to the square bracket P to the E, this does not mean double dualize after raising it to the P to the Eth power or something. This is the ideal generated by P to the Eth powers of elements of I. And so in particular, and the I colon j, this is the set of all things in R such that R times j is contained in I. All right, so let me just tell you what this is in one quick example, and then I will stop. I have 1 minute left, it looks like. So let's do this elliptic curve, cone over the elliptic curve example. Okay. So maybe F, I mean, maybe it's like zy squared, I don't know, x times x minus lambda z, x plus z. So this is like this is the equation, this is the homogeneous equation of an elliptic curve, right? Okay. If I let I be the ideal generated by F, so I'm going to look at kxyz mod I, and I want to ask whether that's F pure at the origin or not. And so what Fetter tells me to do, and again, this is for all E or some E, they're equivalent. Do it for one bigger than 0. Do it for one E, you get it for all E, vice versa. So if I have I equaling F, then if I take F to the P minus 1, okay, I guess and then I'm asking, that's something, I'll say something about what it looks like in just a second, and I'm just asking whether this is in x to the P, y to the P, z to the P, that's my maximal ideal of interest in a cone, or not. Right? Okay, now if you just look at the degree here, this is a degree 3 thing. I'm raising it to the P minus 1. the only term that's going to matter in this guy at all is going to be x to the p minus 1, y to the p minus 1, z to the p minus 1. There might be some coefficient in front of it, and then stuff. And the stuff doesn't matter. It's all going to be in there. And so all we would have to do is figure out whether this term exists as a non-zero coefficient. And again, if you like look in Silverman's book, I'm out of time, so I don't want to go too much into it. But you know, I'm giving the Hasse polynomial up to some homogenization. This is exactly what you do to compute whether an elliptic curve is ordinary or not. And so it's just computing this coefficient right here. Okay, and so that's exactly, that links us back here. But on the other hand, this gives us a very quick way of checking like Frobenius splitting of a lot of varieties. And I'll say a little bit more about this and why it's actually effective in some cases tomorrow, because I really will talk about like going from characteristic P to mixed characteristic to characteristic 0. Okay, thank you very much.